Yeah. So we have a bunch of apps. They're very big. Kaiching is used by some immense proportion of Singaporeans, somewhere around 50%. They have no idea they're using a near blockchain. HOT, all these kind of things are sort of, actually, I think they're quite a lot larger now than they were when I made this slide. And the reason for that is we make it really, really easy to onboard. You don't need to go out and find gas. You don't need to get 12 words and write them down, and don't tell anyone those words, but also, tell us the word occasionally. And yeah, so we have a account model that works really well for us and allows us to expand to this kind of size. But as an industry, we have this terrific problem, which is that all the applications are really, really fragmented. So we onboard people, they use one of these main apps, and then they kind of largely abandon their account because each chain is good at something. So, Ethereum is great for exchanging value. Solana is great at weird trends. Monero is great if you want to do things privately. But we have no way of getting a user from our applications to anyone else's applications. And all that onboarding they go through on our side is not useful anywhere else. So in the attempt to solve that problem, this is how we do identity generally. You sign in with an email and password. You sign in with Google. You sign in with Facebook. And we use the OAuth tokens generated as a way of basically finding your private keys. So yeah, how do we do this sort of cross-pollination? The idea we came up with was chain signatures. Now, chain signatures is terrifically simple. All we do is every single user account, we put a private key inside of there. And so if you are in control of the account, you're in control of the private key, and the private key never changes. Now, putting a private key inside of a smart contract, terrifically easy. Keeping it private, very, very hard. So what we do is we use an MPC process, very standard, very boring. You could have written the thing in 1990, and it would have worked just fine. But yeah, we have a series of MPC nodes. Those MPC nodes watch the chain, and when certain actions are taken, when this function is called, it will return a signature using the curve the user selects. Very, very simple API, but what can you do with it? The technology itself is not interesting, but what can you do with this thing? We make sure we keep the signatures the same, even as nodes go in and out, using resharing, using sort of an MPC dealer. And what do we do with it? The first most obvious thing is multi-chain paymasters. So one of the biggest problems with onboarding is that you have to find gas on the chain you want to use. Now, a paymaster, for those of you who don't remember right now, is this is a big sort of thing on Ethereum, is that when a user normally interacts with the blockchain, they pay for their gas, and they get some sort of service provided to them. What a paymaster does is allows a sponsor to pay for the other person's transactions without them needing to pay necessarily. Now, generally, sponsors are people who run applications. Application runners have found that they lose sort of tens of dollars of users over cents of gas. So we built this system on Near, which is fairly useful. And now we're porting it over to all the other blockchains that exist. So when you have a private key inside of your smart contract, what you do is, traditionally you would pay the gas using the key, the funds inside the key. But instead, because you have programmable keys, what you can do is you can promise not to use this key to drain the account by sort of showing the code that governs that key. You can have a sponsor elect to pay for individual transactions, and then the user has no concept of what network they're on or what gas they're using. We find that users generally don't care what chain they're using, and the quicker we can move them from one to the other, the better. What this allows for is pay for gas with anything. So you don't need to know that you're using a chain on Ethereum or Sweat or anything like that, provided you make a payment to an individual who's willing to sort of pay you back in gas. You can do this with it wherever you like. And this sort of, so generally we found that it was about, if you have to get the correct set of gas, it normally takes the average user about 2.5 hours to bridge it to the correct chain. And it's sort of about 10 or 15 steps, and we found an attrition rate of roughly 97% when people are trying to find the right type of gas. So this means you can drop onto any application and use it without thinking about what the application is. Now the next thing up is wrapping keys in NFTs. Now, I can see people's eyes glazing over a tiny bit because NFTs are the least interesting and least academic part of the crypto industry. But what they are is a very well understood abstraction. Right now, Near and various blockchains have very mature industries for lending against NFT keys, selling NFT keys, dropping NFT keys, which is dropping an NFT key is where you give someone a link and they claim an NFT. Now, when you start putting keys inside of NFTs, what that allows you to do is, if you want to send someone Bitcoin, you send someone Bitcoin to an NFT key, you then send them a message on WhatsApp, and they claim that NFT key and immediately claim that Bitcoin. Now, this seems like a very simple use case, but we did some trials of trying to use USDC as a replacement for local currencies in countries where the financial system has collapsed or is sort of in a really bad state of things. And we found the process of people setting up wallets to use these things was just terrible. And we once again had incredible attrition and no one was able to use it. Lending against keys is very, very useful because what it allows you to do is it allows you to have your assets, not change any of those assets, not do any transfers. And because you have a sufficient amount of assets, say Bitcoin, Ethereum, all this kind of stuff, you can take actions on other chains whilst gradually building up a bill, like you would with a phone bill, in a decentralized manner. And people are willing to lend a certain amount for each key, and you have to pay it back at some point, like the end of the month, with a small amount on top of it, which once again gets people using this stuff. So this is all sort of very practical and very boring. But when you assign the right to sign with a key to an NFT, you also get the next obvious step, which is key markets. So key markets are incredibly simple. I have a key with Bitcoin on it, you have a key with Ethereum on it, and we swap the ownership of those keys. And this allows sort of gasless transactions between any arbitrary chain with any arbitrary asset. So this allows you to do decentralized finance in such a way where I can say, look, I have some Bitcoin, I want any arbitrary asset on any arbitrary chain, and market makers can fill it immediately. And this is the full sort of centralized exchange experience, but with no gatekeepers, no sort of KYC, and that means that you can immediately have the asset you need to do the transaction you want to do without really thinking about it. So there's lots of sort of weird stuff like, if you have wrapped Ethereum on Polygon and you want USDC on Near, how do you do it? Well, you probably don't care. You probably just care about what the sort of notional value of that token you're using is. So what we're doing is we're making, we hide this all behind sort of user interfaces, but what we're trying to do is we're trying to make it so you just care about how much money you're spending, not what type of money you're spending. Much like when you go into a shop and you spend your credit card, it doesn't really matter what country you're in, you just pay for it using your balance. Next up we have, there's a lot of applications and a very short talk. It's a bit of a whistle-stop tour of what we're doing here. The next thing up is smart contract-owned domains. Now, people spend a lot of time making their smart contracts decentralized, secure. They audit them. They have these beautiful governance systems. And then someone loses the keys to their Cloudflare account and everyone gets rolled. And there's sort of, every year, there's about $1 billion worth of hacks, which are just due to someone losing control of the front end, which is sort of really, really nasty. And the other side of this is generally, front ends and back ends of applications are incredibly tightly paired. So whoever controls the front end has a great deal to say about what happens on the back end, which sort of takes away that notion of decentralization. And what we're attempting to do here is make it so you can define using a smart contract what assets can be served from a domain using some very, very simple technologies that works in every single browser. The reason this is useful is that currently when you design an application, the front end has to be basically entirely untrusted. And that means that you need to have a front end, you need to have a wallet to sanity check whatever it is the user's doing, and then at the end you need to have the application itself. If you can trust that the code being served has been approved by the relevant smart contract, you don't need a wallet in the middle because it's just one application. And this solves a lot of like really nasty UX problems involving sort of confirmation and explaining stuff to people that is probably not really relevant to what they're doing. So if you sort of have a USDC bank account, you probably don't want to be explaining to people like, hey, this is going to cost you you probably want to say this is going to cost you 1 cent, rather than explaining this is going to cost you 1 cent of near, and you need to do a transaction, and this transaction is going to do this. It's all sort of superfluous information. And once again, we saw that the first time people saw wallet confirmations, we saw about a 30% rate of attrition in people using this thing. This is the whole sort of the thread running through this whole idea is how do we make it so we don't lose everyone trying to use a decentralized application? Because people just aren't you won't get any kind of widespread adoption without sort of widespread usage. So how does it work? We use DNSSEC and SSL and something called signed exchanges, which is this awful technology Google made for Google AMP back in sort of 2010. And what it does is it allows third-party entities to have signed bundles of assets, which are signed using the SSL key, and then the person serving those assets doesn't need to have the SSL key. So what do? We have the SSL key signature be done using the smart contract. And that means each time you want to deploy a new front end, you get it signed by the smart contract using whatever governance system it is you do when you update your code. And then any entity can serve it. So you could have a censorship-resistant system where you whack up your DNS record, you say there's 100 possible servers who could be serving this thing, and if any of them try and serve any asset which has not been approved by the smart contract within its sort of expiry period and all that kind of stuff, you'll get an SSL certificate error, meaning which generally scares off users relatively well. So we're really excited about this technology. That's coming out in about a month. And we think it's going to make it so people can have sort of really trustworthy front ends on any application on any chain. Next up, we have encrypted content on chain. One of the big problems in decentralized applications is that everything has to be public, which locks out a lot of things like content creation. So if you want to sell a book on chain, right now it's almost impossible. So what we want to do is basically have the ability for a smart contract to encrypt and decrypt content whenever it wants to do that. Now, there's some really good pioneering research by Dfinity that did a version of this. We're potentially doing something much dumber, which is we are sharing signatures. Generally, the MPC node service generates a signature by sort of communicating with each other in a decentralized manner. Instead, they'll be communicating directly with the client, and that allows them to generate a signature privately on the client side. And then what we do is we use that signature as a deterministic form of entropy to generate a private key. That private key then symmetrically encrypts whatever asset you want to put on chain. And that allows you basically to, in this case, write a book. And whenever anyone pays you 10 USDC, they will get a copy of that book and the decryption keys necessary to read it. This opens up there's lots and lots of content creation stuff, which is very, very useful for this. But I'll get onto the slightly more interesting sort of end game of this technology. Encrypted content is cool. And now we're getting into the future. This stuff is, everything before this was stuff that's out or coming out in a month or two. This is kind of where we're going in the next 6 months, which is we are planning to make it so you can do basically computation that no one else can see. And this is sort of, to some extent, the holy grail of blockchain computation. Now, it sounds like we've solved fully homomorphic encryption. I'm going to tell you now we haven't. We have a much worse solution for it. But what we're trying to do here is so the first thing we have is we have the ability to encrypt things on chain. The second thing we have is we have the ability for smart contracts to decrypt things. Now, that's great for things like WhatsApp. It's great for sharing photos. It's great for sharing videos. But if you want to mutate things, you're going to have trouble. So what's our solution? I'm sorry. We're using, very, very quickly, we're using ZK proofs on the client side. Basically, the client downloads, the client runs a VM with a ZK proof. They run the code, and the code says what you can read and what you can write from. Initially, you start with an empty set. You then do validations of local data, for example, an OAuth token, to prove some form of identity on your local machine. This makes it much easier to program. It makes it private. And it makes it very, very simple. What this generates is a trace of things you can read and things you can write, and a proof associated with that. With that, you can go to the signing network. You can get an appropriate set of decryption keys for the stuff you want. You can then get a new set of re-encryption keys. and then you can send your you can do a provable transition from the encrypted data to the newly encrypted data, send it up on chain, and you can generally run applications using a standard VM. And I think I'm entirely out of time. Thank you so much, everyone. And are there any questions very quickly?
Who has questions? So I have one. When you said, when you talked about the solution with the DNSSEC, can you quickly elaborate? Like, who is in control of the DNSSEC key, and it protects you against what kind of attack?
Sure. So it's not a complete panacea, but what it does is the first thing you do is you whack up so you have a DNSSEC record, which is signed by the smart contract. Now that DNSSEC record has an incredibly high expiry time, an unadvisedly high expiry time. And you pair that with SSL certificates of assets. And in the DNSSEC record, the DNSSEC record is basically so you can choose who can and can't read, who can and can't serve the assets in a decentralized manner. And it protects you against certain types of attacks, but it doesn't protect you against, for example, the domain expiring. But what it does is it gives you transparency over who can serve the assets. And then with the SSL certificate, once again, it gives you provability if someone is behaving very, very badly. So it's kind of more defense in depth rather than being a perfect panacea. But it means if you want to do these kind of attacks, it takes a much longer period of time, and you've got to plan much better. And it sort of shrinks the windows for those sort of attacks.
Thanks. Any additional questions? Yeah.
Yes, maybe one for the last slide that you showed. So, because you said you generate some keys here with the read and write access and so on, and encryption, get new encryption keys. So what's the and you're saying that you're combining this with a proof such that it is still verifiable what the user has read or writes. So can you say what kind of computation trace you do on what kind of information? So are you what's the circuit of the proof doing?
Sure. So now this is I feel I'm not the ZK guy on my team, so I apologize if I don't use the terminology correctly. But basically what we do is we have the computation has the signature of round. And this is hidden that relatively well behind libraries. But what we do is each computation is from an input and a list of things you can read. So that's sort of taken from the last round. And you previously have, so I guess I should probably start at the output. You have a proof of a computation that is valid, that you have the right to read a set of things. And then you go off to the chain encryption system and you say, hey, look, I have a right to read these keys. Can you give me the keys that would allow me to decrypt the content within those keys? You then get those keys back, you decrypt them, and then you run a program which generates a zero-knowledge proof from those set of keys to the new set of keys you want to write, so the things you want to write, and the next set of things you want to read. So you can see sort of a trace of what the output of this is. Now this is obviously an applicative computation, so you need to sort of stop each time you need to read something new or write something new. But yeah, it's sort of relatively general and relatively simple.
Thanks. So let's thank our speaker very much.